That's right.
Recording is on.
The people in Cambridge in the very south, they kind of exaggregated the distances in the south, which of course are the areas that the participants are familiar with, right? Whereas the people located in the north, they kind of fell for the opposite bias, right? They shrank everything in the south because they simply weren't that familiar with it. And of course, if we have this meta representation of reality, right, then depending on our experience, we're going to have a very different mental representation. And that is something that's going to bias our decision making. So I would like to claim that we have exactly the same biases in software. Potentially, they're even worse because software is incredibly complicated. So the first challenge that we address with the behavioral code analysis is to get what I call situational awareness. What does our software actually look like? Where are the weak points? Where are the strong points? From a couple of different angles that I'm going to show to you soon. So looking at the software system, answering questions like that are not easy. Because we might have multiple different subsystems. Those subsystems might be developed by different people organized into different teams. So it's very likely, if you go into a typical software shop, it's very, very unlikely to find a single person that kind of knows it all, right? We tend to have different areas of expertise. Now, think about that experiment I showed you just a minute ago. It's exactly the same thing here in software. If you try to draw a map over your software, that map is going to be heavily biased by the parts that you're experienced with, the parts you're familiar with. And of course, the software system doesn't stop at its boundary. We typically have different integration points. We have different clients. We have mobile applications. We have other machines using our system over different interfaces and so on. And this kind of adds to the picture. So if we pick up a typical software system like that, how long will it take us to answer questions like these? Do we have any technical debt in that system? Are there any potential problems that are holding us back? More importantly, where are those potential bottlenecks? And what kind of bottlenecks are there? And then how do we communicate something as technical as technical depth or code quality? How do we communicate that to non-technical stakeholders? I like to view software development as it's largely a challenge of communication, right? We technical people, we need to take something as deeply technical in code and explain it to non-technical stakeholders. And it's a challenging problem. And that's actually where I started to work with what eventually became behavioral code analysis. So you might be familiar with traditional code analysis and traditional code analysis tools. And I'm actually quite a fan of traditional analysis, different static analysis techniques. I use it almost on a day-to-day basis. And those kind of metrics, source code metrics, are really, really good at their purpose. What they're not good at is to communicate things like this, like technical depth or identifying bottlenecks. And I would like to try to explain why that's the case. So let's discuss technical depth and what I call the perils or the dangers of quantifying technical depth. Because over the past 5 years, I think that I worked with, I probably analyzed between 250 and 300 different code bases. So I analyzed lots of different code bases by multiple different organizations around the globe. And one thing I quite often see is that many organizations, they tend to have some kind of problem with technical depth. They're kind of often noticing the symptoms, and they're typically noticing that their development tends to be quite unpredictable. It's very, very hard to guess how long something is going to take. They might also see that their external quality becomes unpredictable. And with that, that simply means what the end users see, that the bugs start to slip through, they deliver a new feature, and suddenly they broke 3 existing features. Or they might have what's typically called an efficiency problem, that you hear cries for, we need more developers, we need 20 additional people by next month, things like that. And quite often the root cause is technical debt, and I'm going to elaborate on that later. So what people often do in those situations, what I've seen many, many times, is that they try to quantify technical debt from source code. So they typically take a static analysis tool, scans the source code, and looks at the findings and sums them up. And I promise you, if you do that on an existing code base, a non-trivial code base, I promise you that you're going to find thousands of issues. If you haven't used static analysis before, you're going to find thousands of issues. So what do you do in that situation? Let's say that you end up with 7,000 issues. The first thing is that you start to prioritize based on the severity, because that's the information you have. So you say that things like suggestions or recommendations, let's just throw that away, right? And then we have the warnings. All right, maybe we can live with the warnings, so throw them away too. So that leaves us with like the major severe issues, right? And you have thousands of them. So what do? You cannot attend all of them at once. What tends to happen is that companies set quantitative goals. So they might have a goal where they say, like, we're going to invest 3 months into paying down our technical debt, and we're going to go from 7,000 major issues down to 5,000 major issues. When I hear that, I always advise against it. Because to me, going from 7,000 major issues down to 5,000, it's, a little bit like choosing to jump from the 5th instead of the 7th floor. It's most likely none of them are a good idea. And there's a reason I say this. Because what we need to do is we need to consider what kind of behavior do we reinforce when we put a quantitative goal on things like technical debt. First of all, what's going to happen is with an incentive like that, people, what we're going to do, and this is a very human thing, is that we're going to pick the tasks that we are most familiar with, the tasks that might look the easiest to us, rather than the ones that might be most important. Again, the tasks we choose are going to be biased by our prior experience. And there's nothing that kind of looks across the whole product. And then it's also the second thing, that what tends to happen with the quantitative goal is that the most important aspect is absent. The most important aspect in technical debt is actually the business impact. So what I would advise instead is that you focus on paying down the technical debt with the highest business impact. And then if that means fixing 10 or 20 or 2,000 issues, that's secondary. That's not the important thing. So what I'm trying to say with this slide is that, to me, quantifying technical debt might be interesting. It might be interesting to quantify it in terms of number of issues or number of outdated components and so on. But that in itself simply isn't actionable. We cannot act upon it because there's too much information, so we kind of need to prioritize. The other problem I wanted to raise was that technical debt simply cannot be calculated from source code. And I'm telling you this because there are methods out there. There are even tools that try to put the monetary value on the technical debt that you have. So you might find numbers like you have 200 years of technical debt in that code base, or 5 weeks of technical debt in that service. And I think this is simply a misunderstanding of the concept of technical debt, because technical debt is not, I repeat, it's not the cost to fix the code. Technical debt is the additional time that we need to spend on features, debugging, onboarding, and roadmap delays, and so on. That's the cost of technical debt, not fixing the code. That said, there might be value in those kind of metrics because they can kind of help us guess or estimate the time it costs to actually pay down some debt. But that's a very different problem that comes later. Now, I still consider it critical for all software products to kind of have a clear inventory and list over the technical debt that is actually driving our costs. And the reason I say this is because there's always going to be a trade-off between improving existing code versus adding new features. And this is a trade-off that balance between new features and improving existing code is something that's going to shift over time, depending on where we are in the life cycle of our product. So it's something that we need to get up to date every now and then. So with all of that said, how do we prioritize? Well, behavioral code analysis offers one perspective, or a very different perspective. So let me try to define what behavioral code analysis really is. And I actually like to start by quoting myself from Software Design X-Rays, and I think this is really, really important, and it kind of sets the context for what I'm going to show you soon. Because to me, behavioral code analysis has never been about any silver bullets. Behavioral code analysis alone won't fix any problems. It might bring you a lot of valuable information that you couldn't have otherwise, but in itself, it's not going to change anything. It needs to be acted upon. And as such, I also don't think that behavioral code analysis really replaces anything. Behavioral code analysis is something that complements your existing expertise, your experience, your knowledge. And the main value proposition of behavioral code analysis is that it helps you focus your attention and your precious time to the parts of the system that are likely to need it the most. And let me clarify that when I talk about the system here, I mean the combination here of not only the source code, but also the people that work on it, how they collaborate, the processes, and of course the context of your whole application. We simply cannot reason about something as complicated as software from just the source code. So the foundation for behavioral code analysis is that, behavioral code analysis, the code is important. It's one of the inputs. But a behavioral code analysis puts much more emphasis on the organization behind the code. And a behavioral code analysis is about us. It's about how we developers, how we communicate, how we interact with the code we're creating. Code base looks like. The way you read this visualization is that each one of these circles, they represent a particular top-level folder. So if this was one of your code bases, then you would recognize the different names here as important subsystems or high-level components. Now, the reason I start with Protobuf is that it's a polyglot code base. So I can click here on the Program Language tab, and I can see which implementation language is used for each component. So just to show you an example, so this is Protobuf, the very core of the application. And we see inside it, we have a bunch of other smaller circles. I can click here, I can zoom into that level of detail, and I see here that each file is visualized as a circle as well. And the interesting aspect here is the color, because you see to the right, you have a legend that kind of shows that this deep blue, that's C++ code. What else do we have? We can zoom out. Here's an interface towards JavaScript, and we see that it's, of course, implemented in JavaScript itself. Same thing here. Here's a Ruby adapter. And, we have it in, it's implemented in Ruby, and so on. So what I want to show you with this is that the behavioral code analysis, it's language neutral. It works no matter what programming language as you use. So it's really nothing special about C++ or C# or JavaScript. And the reason behavioral code analysis works across different programming languages is because it's based on version control data, and version control data is language neutral. So With that said, we can do something called a hotspot analysis across a code base. Now, what is hotspots? Well, let me try to walk you through it. It's still it's the same kind of visualization, right? I just shifted the perspective to show a different aspect. So we have the different top-level folders here. I can zoom in on them, and I see each file visualized as a circle. You see that the circles here, they have different size. So size just represents the number of lines of code. So the larger a module, the more source code we have in it. The important aspect is the color. You see some are more red than others. And that's because color is used to represent change frequency. That is, how often have we, as developers, worked with that part of the code? How often has the organization made a change to that part of the code? And sorry, my 5-year-old just got here and wanted to say hi. Here comes up. All right. So it's always exciting to work from home. So what we refer to as a hotspot in behavioral code analysis are these large red circles, the parts of the code that has the most development activity. Now, there's a reason why I find hotspots fascinating. We can look here. I'm actually filtering the map a bit. I'm going to turn it down so we can see all source code. As you see here, most of the code in Protobuf is not a hotspot, right? The hotspots seem to be limited to a part here of the C# core and the core of Protobuf. Most of the code seems to be relatively stable from that perspective. And this is something I've found in every single code base that I've analyzed. And I want to show you one of the most important graphs in behavioral code analysis. So I'm going to shift to something, this is just some descriptive data. So if you look at this graph, what you see here on the x-axis is each file in this code base. So each file in Protobuf, and those files are sorted according to the change frequency. How many changes, how many commits have the development organization done to that particular file? And the number of commits is what we see on the y-axis. So I can zoom in at a part of the application here. And what I see now is kind of fascinating. It turns out that most of our code in Protobuf is here in the long tail, right? That's where most of the files are. That means that's code that's fairly stable, code that's rarely, if ever, changed. And if we talk about things like improving existing code or redesigning software, well, maybe this long tail here, maybe that's part of the code where we can live with some quality issues. As long as that code works, maybe we could just live with a certain amount of technical debt there because the code is so stable. On the other hand, what this graph shows us is that most of our development activity tends to be in a very, very small part of the code base. And this is the part of the code base that's identified by the hotspots. And the thing with technical debt is that even a minor amount of technical debt in a hotspot can quickly become really, really expensive due to the high amount of development activity. So let's dig a little bit deeper into this. Let me switch to an even larger code base so we can see this at scale. Let me switch to the .NET Core Runtime from Microsoft. So we see here on the CodeScene dashboard that this is a pretty large code base, almost 9 million lines of code, 8.6 million lines of code. And it's being actively developed by almost 200 people. So over the past month, we had 200 contributors in that code base and 8.6 million lines of code. Now, given that you have 9 million lines of code and 200 developers, who do you think has the overall picture? Probably no one, because even if we understood all the details of the .NET Core Runtime, it would be virtually impossible to keep up with all the changes that are going on by having 200 developers working in parallel on that code base. So the reason I shifted code base here was because I really like to show this at scale, because I think a behavioral code analysis, the larger the organization, the more important that we have the situational awareness that we get. So let's go into the .NET Core Runtime and let's look at the hotspots in .NET Core. Here we go. Again, I'm filtering the map a little bit to show the most relevant parts. If I include everything, we're going to see a lot of data here. Let's see, my screen is really lagging now. Here we go. So, as you can see here, again, let's zoom in a little bit. So the structure of .NET Core, we can see we have the libraries here, and we see there's one very clear hotspot inside the libraries. It's something called system_runtime.cs, so a C# file. We can also see in Mono, there seems to be a cluster of development hotspots here inside the mini package in Mono. And we also see a very clear cluster of hotspots in the C++ part, core CLR. So that's what I want to zoom in on. So let's click on that one. And we can see that most of the hotspots tend to be clustered in the GCHeap package. So that's the just-in-time compilation component of the .NET Core Runtime. What this means now is that the parts here in the JIT package, those are the ones that are at the head of that parallel curve I showed you earlier, right? The parts with the most development activity. So these are the parts I would like to sample for any potential code quality issues. And this is the first thing that hotspots do for us. They take a large code base, then they narrow it down to much, much smaller part, often as little as 1 to 2, maybe 3% of the total code base, and say, please, focus here. This is where you need to pay down technical debt if you want to become more efficient. So you don't have to fix all those 7,000 major issues. I would start by focusing improvements to the hotspots. Now I'm going to get back to .NET Core very, very soon. Before I do that, I want to show you what might be a limitation of the hotspot analysis. So let's get back to my slide deck so I can show you something else. So even though a hotspot analysis can take a large code base, 9 million lines of code or 1 million lines of code, and narrow it down to a few hotspots where we can focus our attention, that still doesn't always solve all problems. And this is obvious in a code base like .NET Core. So I've been following the development of .NET Core for a while, and one of the most interesting discussions on GitHub was around this one, reorganizing gc.cpp. Now, what is gc.cpp? Well, it turns out that's the .NET garbage collector. And as you see here in the text, gc.cpp is the whole garbage collector implemented in a single file with 36,000 lines of C++. That's a lot of C++ in a single file, right? And it turned out that this gigantic monolithic gc.cpp turned out to become like a bottleneck for contributors. It became really, really hard to know what responsibilities do we actually have inside the garbage collector. So there is a suggestion here to kind of start to split that gigantic file based on a bunch of different criteria, by function, by class, and so on. And the thing is, if you have something similar and you agree upon it, it doesn't have to be 46,000 lines of code. It's enough that you have a file with 2,000 lines of code. How do you, and you find out that that's a hotspot, you inspect the code and you see there are a bunch of issues. How do you address that? Because to me, trying to refactor or redesign a couple of thousand lines of code at once, it's a huge risk. So again, I try to advise against that. I always try to advise on taking on refactorings and code improvements in very, very small increments. Ideally, something that we should be able to do in 1, maximum 2 days. And refactoring something like this with 36,000 lines of code, what's likely to happen if you start that is that you're going to branch out. You're going to spend months on that branch, and you're never, ever going to be able to merge it back, because in the meantime, all the other developers have been making changes to their original code, and it's just impossible to keep up with that. So when we come across complex hotspots, what I try to do is I use a technique called X-ray. So X-ray is a concept that takes a hotspot, parses it into separate function blocks, and then it looks at the commit activity and aggregates that on a function level. So X-ray is a way of finding hotspots on a function level. And this is something that we can use to prioritize specific starting point for refactorings or code improvements. So let me show you how that works in practice. So I'm back here to the .NET Core Runtime. I'm zooming out, and I'm looking for gc.cpp. I can, of course, if I want, I can, of course, filter a little bit and find out, there it is, right? But it's also easy to spot from the top level because it's such a big file. Can you see it here? So let's zoom in. Let's click on gc.cpp and see what info we have. We see here that according to CodeScene, the size of this file is 31,000 lines of code. The only reason we have a lower number here is that we parse out blanks and comments and stuff like that and subtract that. And what we can also see, we can see down here, this is something called a complexity trend. I haven't talked about that yet. I can show you some examples later. But it's basically a way of finding out in what direction does this hotspot evolve. I'm going to talk much more about that soon. And here we see it's pretty much a flat line with a minor increase here in late 2019, meaning that the code is a little bit more complicated now than it was a year ago. But I'll get back to that. Now, 31,000 lines of code, way too big for refactoring. So let's prioritize using X-ray. And in CodeScene, all I have to do is I click a button here that says X-ray. And behind the scenes, CodeScene is going to parse this gigantic gc.cpp. It's going to parse all the historic revisions of that file and look at which function was changed in each commit. And that gives me hotspot on the function level. So the way I read this inside gc.cpp is I have this list of hotspots on the function level here, and they are sorted according to the change frequency. How many commits have we done here? And the reason the X-ray works so well for prioritizing starting points is, if I show you a different graph that should look familiar, let's look at the change frequency distribution on function level. A couple of minutes ago, I showed you how this looks on a file level. Here we have it on a function level. And again, we see it's a Pareto distribution. It's a power law distribution, meaning that most of those 36,000 lines of code seem to be stable. They are here in the long tail. So maybe that's clearly not code where we should focus our initial refactorings, right? That's probably the code that's stable and just does its job. It works, it's battle tested. So let's just leave it as is. Let's instead focus our investigations at the head of the curve here. And this head is what the hotspots identify. So let's get back here. And in this case, the first, if my task was to somehow refactor gc.cpp, what I would do is I would definitely focus on the initialize function here because it's being worked on the most. It's a fairly large function, 406 lines of code. So 400 lines of code, that's a lot for a single function, isn't it? It is. But it's definitely less than 36,000 lines of code, which is total file. And it's definitely less than 9 million lines of code, which was size of a total code base. So more important, I'm now at a level where I can act upon this information and I can do a focused refactoring based on data from how we, as an organization, have actually worked with the code so far. Now, from here, I can, of course, look at the source code. I can pick it up so we get to see a little bit of C++ code. And let's see, here we go. So this is the initialize hotspot. And you see it's a very tricky code with a bunch of nested conditionals all along. And what I typically do when I refactor is that, and I'm going to just share my general principles, is that I always look to increase the modularity and try to encapsulate concepts. So when I do a refactoring, I try to do them iteratively. So in the first sweep through a function, I'm not so much after perfection. I'm more after taking the code to a specific state where more real, more deep refactorings can be done with less effort and a more controlled risk. So I typically start by extracting a lot of functions here, try to modularize this piece of code. And by just looking at it, what I typically do is I identify patterns like this, where I have a specific condition. If that is true, I do this, otherwise I do that. So that typically, to me, sounds like two different concepts. So if this was my code, what I would probably do is I would start to extract them into separate functions and put a name on them. And I'm going to talk about that in a minute, why I think that's important. So by doing that, I'm going to simplify the overall solution. Then I might look for more complicated conditionals like this. I might even encapsulate them in an inline method or something, just to kind of put a name on that condition. What does it mean from a business perspective? What does it mean from a requirements perspective? And then I always look to kind of collapse and simplify conditionals, because conditionals are one of those things that put quite some cognitive load on our brain, right? So I will look for things like this, where this one is interesting, by the way. If you can see the code here, you see we have a condition here. If it's a heap hard limit, we do something. In the next if statement, we again check, is it a heap hard limit? Then let's do something else. So these two can clearly be collapsed into the same condition, right? We can get rid of one condition immediately, very low risk. And after that, I would maybe say that, all right, so maybe a heap hard limit, maybe that's could be better expressed as using the strategy pattern, for example. So I can get rid of the conditionals entirely and isolate that behavior in a separate entity. All right. I don't want to spend too much time going through the code. There are probably other people that can do it much, much better than I can. Just want to give you some examples what I typically look for. The reason I try to modularize our hotspot is because I'm always trying to reduce the amount of branches in the code. I mean, to a certain degree, I always try to be pragmatic, right? Sometimes the if statement is just what the doctor ordered, right? But in particular, when I come to really huge numbers. So if we see here, we have a column here on this hotspot that says cyclomatic complexity. So cyclomatic complexity is one of those really old complexity metrics from 1976. And it's a metric that's very often misused. It's a pretty rough complexity metric. The reason we have it in the X-ray in CodeScene is because cyclomatic complexity is a very good estimate on the number of unit tests you would need to execute all the paths in this initialize hotspot. So it basically shows us that we need 63 unit tests just to test the initialize method. So that kind of tells us something about the complexity of that code anyway. All right. I see that time's flying. I want to show you something else. I want to show you how you can narrow down and save a lot of time in your investigative efforts. Because using hotspots and X-ray, we can quickly zoom in on the parts of the code that tend to be the most important to us. What behavioral data alone cannot tell is if we have a hotspot, is it also a problem? Because sometimes you come across code bases where the top hotspots actually look quite good. And when that happens, you're actually in a very good position, because it means the code you work with the most is also code that's easy to modify and easy to understand. So what we've been doing in CodeScene is that we have introduced a concept that we call code health. How healthy is your code? And the code health concept in CodeScene is based on a bunch of different factors. We basically identified, depending on programming language, 25 to 30 different metrics that all correlate with the increased maintenance costs and an increased risk of defects. And then we talked CodeScene. We wrote detectors in CodeScene for all those different rules. And then we have an algorithm based on a lot of baseline data that can kind of take the scores on all those different code smells and potential problems and weight them together to a normalized range of 10, which is the best, down to 1, which indicates severe maintenance problems. And by doing that, you can kind of get some kind of, I really don't like the word code quality, but it's almost like you can get a very quick assessment of how healthy is that hotspot. And that can quickly help you to identify refactoring candidates. So let me show you how that looks. I'm going to switch to a different code base here. I want to look at another large-scale code base. I want to look at TensorFlow from Google. So TensorFlow is on a machine learning platform for building deep neural networks. And you see it's also a pretty big code base, right? Almost 3 million lines of code, close to 400 developers working on that code base. So lots of development activity. Meaning if the hotspots are problematic here, then we might have an issue. So let's zoom in and have a look. I can, of course, start from the hotspots, just like we did before. And I typically always do that when I come across a new code base, because it kind of helps me to see patterns. Do we have any clusters of hotspots and stuff like that? But once I have that familiarity with the code base, I tend to operate much more from the dashboard here, because CodeScene can already identify the top hotspots and filter and sort them out for us. So I get the list of the hotspots here. And if I click here, I can see the code health score of each hotspot. So let me show you how that works. So code health, remember, it's an aggregated metric, 25 to 30 different aspects that are calculated, weighted together to the range 10, the best and healthiest code, down to 1, indicating severe problems. And what we see here is that one of the hotspots in TensorFlow is a C++ file called import model. That kind of sounds important for a neural network, doesn't it, right? So this is most likely a business critical part of TensorFlow. And we see here that in 2019, import model had a code health score of 6. Now, people often ask me, what is a good code health score? Do I have to achieve 10? And I don't think you have. I don't think it's important what the absolute numbers are. As a rule of thumb, I would say that on a code base that's being actively developed, meaning you add new features, I would prefer a higher code health, 8, 9, or 10, so fairly high. On a code base that's more in a stable maintenance phase, like, for example, Core CLR that we looked at earlier, the garbage collector, maybe I can get away with the lower code health. Maybe I can get away with the code health of 5, right? But so TensorFlow with the code health of 6 a year ago would probably indicate that this is a part of the code where we might want to invest in improvements. But like I said, I'm not concerned with absolute numbers. I'm more interested in the trends. Is the code getting better or worse? And we can see here that over the past year, something dramatic has happened. Import model went from a code health of 6 down to 2.7, and it seems to have stayed on that lower level. The reason I focus on trends over absolute values is because trends are actionable. If you talk to a non-technical stakeholder, no matter what they tell you, and no matter what level of technical depth you have, no one, I really promise, no one wants the code to get worse, right? So showing a trend like this should immediately get attention, because this means that the part of the code that you work on the most, the hotspot, is declining in code health, meaning that it's more challenging, more higher risk, and harder to work on that code. So this is something that we would like to catch. From here, if this was one of my code bases, I would dig deeper. I would look at the virtual code review in CodeScene. I can, of course, do that. So the virtual code review basically presents some of the findings behind the code health metric. It explains, I'm going to give you a few examples later. It explains where those potential problems are, what those potential problems are, and so on. Another interesting thing with version control data is that we can immediately find out which developers, which teams have worked in this code. So I can see who has written most of the code here. And again, if this was my project, those would probably be the people I would talk to get more input before making a decision what we do with this hotspot. And finally, I would also like to introduce you to the complexity trends that I skimmed over when I showed you gc.cpp. So complexity trends are often correlate with code health, but not always. A complexity trend is a lightweight version of code health. It's a way of showing, is the code getting better or worse over time? And the way CodeScene calculates this is that it picks out each historic revision of that hotspot, and then it calculates the number of lines of code over time, which is what you see here on the yellow line. So we see the number of lines of code, it's growing, it's growing, it's growing, we get more code. And then it also calculates the complexity, that is how many logical levels of indentations, basically how many nested if statements you have over time. And again, we plot that like this, so we can see that indeed the complexity seemed to increase quite steeply here over the past year, which kind of again is reflected in the declining code health score. And then, of course, if I decide to do something about this, I always have the X-ray analysis, and I can go in here and I can find a starting point where do I start focusing improvements. So that was a very quick tour of how I investigate hotspots. There are a few other things I would like to point out to you. Let me ask, before I go on, can I ask the organizer how much time do I have left before we want to shift to a Q&A session?
So I see there are quite a few questions. I also posted some questions, but not many upvotes. So it's hard to determine how much time we need for the Q&A, but it will be prioritized anyway. So I would say just continue. And then with the Q&A session, we will just use the time left to answer the most relevant questions.
Okay, so I try to keep this short. I don't want to take up all the time here. Let me try to wrap this up within 10 minutes, maybe shorter. Is that okay?
I think you can, even 20 minutes is totally fine. We usually have quite long discussions and talks, so no problem.
Okay, good, very good. So before I return to CodeScene, let me show you one more thing related to code health. So the things we focus on when we calculate code health, like I said, those are factors that are known to impact maintainability and the risk for defects and stuff like that. And just to give you a few examples, some of the things are low cohesion. So if you have a module like gc.cpp, how many different responsibilities are actually implemented in that module? Cohesion is might also be a function level issue. So you have a function doing multiple things. If you remember what I showed you in initialize hotspot in gc.cpp, it was clearly the case there that there was a bunch of different things that were going on that could perhaps have been expressed in a different way in the design to keep those different responsibilities more distinct. And that's important. Cohesion is important. It's one of the most important properties of good design, because having responsibilities clearly encapsulated and defined kind of serve as high-level entry points for me as a code reader. And code is read so much more often than it's written. So optimizing for understanding is one of the most important things we can do. So cohesion is one important factor in code health. Another thing we look for are a bunch of different complexity metrics. Of course, we calculate the cyclomatic complexity, but it's weighted very, very low. So if you look at the output from CodeScene's machine learning algorithms to calculate code health, cyclomatic complexity tends to be weighted very low. It has some predictive value, but not that much. Instead, CodeScene tends to punish things like deeply nested logic much more. So let me talk a little bit about deeply nested logic and complexity in general. Because when I do sessions around this, around refactorings, which I do occasionally, I always recommend, just like I did to you when I showed you initialize in gc.cpp, that I try to modularize a complex hotspot. And a common observation is that people tell me that, all right, but are you really improving the code? Aren't you just having exactly the same complexity, only now it's distributed in different functions and files? And it's true from the perspective of the machine, right? It might have the same overall complexity, but I like to claim that from a cognitive perspective, from the perspective of our brain, it's a big, big, big difference the moment we extract the behavior and put a name on it as a function. And the reason for that is something that cognitive psychologists call working memory. So working memory is like the mental workbench of the brain. It's the part of the brain that we use to perceive, integrate, and manipulate information in our head. So working memory, that's what you use the moment you do a reasoning task. So if you play chess, working memory. If you try to solve a Sudoku, working memory. When you try to read code, working memory. So working memory is vital to us as developers. The bad news are that working memory is also strictly limited cognitive resource. There's only so much information that we can hold in our head at once. And you might have heard numbers like 7 plus minus 2, the number of things we can keep in our head at once. That's referred to as the golden number, was defined by a psychologist called Miller in 1957. Since then, cognitive psychology has moved on, and modern cognitive psychology paints a much, much darker picture. It turns out that depending on the kind of information, it can be as little as 3 to 4 things we can keep in our head at once and reason effectively about it. So what does that mean to us as developers? Well, let me show you an example. And excuse me here, because this is actually JavaScript, but it's fairly simple JavaScript, so I think you can follow the overall flow anyway. Let's say we have code that looks like this, some deeply nested logic, and there's a particular function call there. We need to do a change there. We need to change some code down there inside that nested statement. Now, when we do that change to that code, we need to keep 1, 2, 3, 4 different states in our head while tweaking that code. That means that when we're modifying code in a deeply nested context like that, we're operating at the edge of our cognitive capabilities. So it's no wonder that things like deeply nested logic has a very strong correlation to the effects. In fact, there's some very good research on one of Ericsson's large telecom systems, where the researchers find out that roughly 20% of all their coding mistakes were due to constructs like deeply nested logic. So this is some of the reasons why CodeScene punishes deeply nested logic in code, in their code health scores. And another pattern that CodeScene looks for is what I defined as the bumpy road code smell. I have a write-down of it down here at imperial.com. You can check it out. And it's like the deeply nested logic on steroids, right? So it's when you have multiple blocks of deeply nested logic inside the same function, pretty much what we saw in the initialize in gc.cpp. And when you find something like that, it's almost always the case that each one of those bumps, each one of those chunks of logic, they tend to represent a specific concept that could maybe better be expressed in the main function. Because the moment you take that complex code, as long as it belongs together, and you extract it, put a name on it, the name of that function is going to help your working memory work more effectively. Because now all you need to keep in your head is that label, right? That aggregation, that abstraction. You don't no longer need to concern yourself with the details. So this was one example on it. And if I go back to the code here, we can see in TensorFlow here, CodeScene lists some of the issues it has found in the import model. So we see it's a brain class, meaning it does way too many things. It's low in cohesion. We have several instances of deeply nested logic. We have a bunch of bumpy roads. And if I click read more, I get to see the details. So that's how it works. For completeness, maybe we should take a quick look at the code health score of the .NET Core Runtime. So the .NET Core Runtime, I really don't want to bash the code here because I'm very impressed by it. It's clearly a piece of technology that works excellently, and it works for millions of users every single day. I have a lot of respect for that kind of code. I also understand that it's a pretty old code base in a complex domain. But looking at the code health scores here, we see that it's almost all the top hotspots here in the C++ parts, they score in the lowest possible category, meaning that this is code that's going to be very, very challenging for someone unfamiliar with it to maintain. So in a code base like this, and you sometimes come across them, what I try to do is I try to prevent further degradations. And this is something that CodeScene can do. So if I go here, I see I have a danger notification here. Oops, sorry, danger notification. I click view, and I see that I have a code health decline. So right now I have 7 hotspots in this code base that decline in code health. And this is something that's actually actionable. So I can click here. And again, no one wants the code to get worse. So maybe these are the hotspots that we can act upon, the ones that are starting to show a decline. It's not that dramatic here. We see a more dramatic decline down here, maybe. It goes a bit more rapidly. So these would be the ones I would focus on this code base before I start to address the more complex hotspots. So my rule number 0 is always stop the rot before I try to improve something. And of course, CodeScene can take a step further because we have been analyzing so much code over the past year. So we have identified a bunch of patterns as well that can kind of predict if code will decline in code health with a fairly good confidence. So we can warn for that, and that's even more actionable. So we have a warning here that says code health here, prediction, future code health decline in one hotspot. So I can click here and I can send I can see that I have a C# class, and the CodeScene predicts that it will degrade down to a code health of 5 unless we do something. So now I can focus extra attention on kind of supervising that code, which is something that CodeScene could even automate for us if we want. And like I said earlier, I prefer to act upon trends over the absolute values. And the way CodeScene does this is, let me show you the last slide for you here. I'm going to skip a few of them. Is that if you look at the bottom of this slide, you see some examples from GitHub checks. So the way we use CodeScene as ourselves, and the way most of our enterprise clients use CodeScene, is as a quality gate during development. So if you work with things like pull requests, you can integrate CodeScene with pull requests. And each time you open a pull request, GitHub or GitLab or Bitbucket or whatever we use calls a webhook on CodeScene, and CodeScene will scan that pull request and return information like, you know, if you merge this code, you're going to decline the code health of a critical hotspot. You can, of course, also, and you can use that as a quality gate. So this is a way of taking all that information and kind of integrate it in our daily workflow. So instead of having us manually continue to supervise and check the code health, we can have a tool that does it for us automatically. Now, I'm really looking forward to answer the questions you might have. To sum up this session, I want to emphasize that we have really just scratched the surface of what's possible with behavioral code analysis. There are so many other things we can extract from version control data, from Jira, from Trello. There are things like defect trends. We can even reason about things like teamwork. We can identify coordination bottlenecks in our code. And one of my favorite use cases, we can reason about the knowledge distribution in our code base. And if you're interested in reading up on that, I have a lot of material on that in Software Design Express, of course. And I also have a lot of publicly available material at my 2 blogs. I regularly blog at mpr.com as well as adamtornhill.com. And of course, if you're interested in giving CodeScene a try, we have free versions for open source software. So if you work in that space, CodeScene is already free, and it's affordable to private projects as well. Now, before I take the questions, I really like to take this opportunity to say thanks a lot for listening to me. I hope you get something out of it. And I'm looking forward to talk more soon. So thank you.
Thank you, Adam. That was really a great overview. I see that we now have collected a lot of questions. In the demo, I guess some questions have already been answered afterwards, after the question was posed. So I would suggest maybe a more loose kind of discussion where everybody can jump in particular the person who asked the question. So more of a discussion kind of question and answer session. At the top, you can sort the questions by votes. And when you do that, you see there's one vote, one question with 4 votes, the topmost. So I'm dragging that to being discussed. How can you detect code that is rotten enough that people make all kinds of workarounds elsewhere instead of improving the problematic code? I think that's quite interesting, and I wonder what you have to say, Anna.
It is interesting. It happens, right, that you you have this piece of code that no one wants to touch, and you go through all kinds of hops to avoid that. An observation I've done over working with lots of different companies is that behavior is very, very rarely related to the quality of that code. Yes, the code often lacks in quality, but a most important aspect is that most likely it's code that we didn't write ourselves. So what I do when I do an analysis of system is that the hotspots, they're really just one perspective. Another perspective that I'm using all the time is what I call a knowledge loss analysis. So remember, it's Git, right? It's version control, so we know who wrote which piece of code. And we also have knowledge over which people currently work on our team, right? And that means we can find code that's written by people who are no longer part of the team. And we can use that to kind of build a knowledge loss map over our code base to find those parts of the code that are written by someone else who's no longer available. And very, very often, that tends to give a different picture. So what that means is that you can often identify that that code that everyone tries to work around as it being a black hole in the terms of system mastery, code written by someone else. And once you kind of get that information up there, you can communicate with your non-technical stakeholders, and you can kind of explain that because they understand that. They understand that this is code written by someone else. We are not familiar with it. So if you want us to work on this code, we need to schedule some additional time for learning because it's going to take time to work with unfamiliar code. So always combine the technical metrics with what I call a social analysis and show what the knowledge distribution looks like. Did I manage to answer that question, or?
I think that's one very interesting aspect. It reminds me of the bus factor. I don't know if you heard of that. The amount of people that need to drop out that the project or company or whatever is going to pieces. So I guess the knowledge loss, or how you called it, is quite related. I don't know who posed the question. That one can maybe speak up and say whether all aspects have been answered from the question. Otherwise, we'll just continue with the next question. So I move that. But you can, of course, anybody can jump back to it. But I guess we'll now continue to the next question. I think that is, I actually wrote that question, and I think at the end it was partly answered already. So the question is, can a technical debt matrix only be used to find and fix old bugs in the system, or also to detect potential bugs early on, e.g. as an automatic code reviewer? And you mentioned that Quality Gate, I guess that is kind of an automatic code reviewer.
Yes, it is. So if you look at CodeScene, I have on the blog, I have some specific examples on it where you can see it in action. So what happens is that CodeScene performs a code review, right? It accesses a quality gate. It identifies the hotspots that declining quality. There's also a workflow in CodeScene where you can classify code as being more or less important. You can specify different goals on hotspots, and those goals are going to be supervised as quality gate as well. But what we also have in that integration is that we calculate the risk of that pull request. So you get the risk metric, if it's low risk, medium, or if it's an increased risk. And the use case is basically that many organizations, they spend a lot of time doing code reviews. And the people who do code reviews tend to become quite overloaded with requests for reviews. They often become bottleneck. So if you know the risk of a pull request, then you can use it to kind of understand that, all right, this is a pull request that I can maybe just do a quick inspection of and go through a little bit quicker, whereas this high-risk change, maybe we need to be 2 reviewers here. So it's a way that helps us prioritize. The way we calculate that is we're using machine learning to find out. You can think of it like, like companies detect credit card fraud, right? So they look for patterns in your purchasing behavior. And we do the same thing. We look for patterns in how you typically work with the code. And then we find things that deviates from your normal workflow. And we can see if it poses some increased risk. So yes, this is a very interesting aspect of it.
Uh-huh. Okay, I think I'll continue with different questions with 3 upvote, not the topmost, but the one which also has 3 upvotes, but is now closely related. So you mentioned risk. So here's a question: how does CodeScene determine whether a commit is an error-related commit? So I guess that is closely related to how risky the pull request or commit is.
Yeah, so the information has to be there. So typically you have to pull that information in from different sources. The CodeScene cannot take a commit and say this is an error or this is a feature. That information typically comes from a lifecycle tool like Jira, Trello, GitHub issues, Azure DevOps, something like that, right? So CodeScene integrates with all those systems, whichever one you have. And then it knows that this commit is being done due to issue 42, right? And we look in Jira and we see that issue 42 is a bug fix. So now we know that all code related to the commit done due to this issue, they are due to a bug fix. So that's how we figure that out. And that's also something we can use to kind of present different graphs of what happens in a hotspot. Is it mainly, what does the defect trends look like? And we can use it to calculate defect densities and so on. So it's by integrating information from multiple sources.
Uh-huh. I think, if you start thinking about it, there's really such a huge amount of information you can directly read out of the metadata or deduce from the metadata. However, here in the last 2 questions, I'm having difficulties to or let me explain it in another way. So if you have some quite old piece of code, then you can, for instance, see how this piece of code, what effect that piece of code had in the future. Because, I mean, there were 100 later commits made. And so you know whether there were some commits which fixed some bug in that special commit. But if you do a new pull request and use CodeScene as this kind of quality gate, then you do not yet have that kind of history. So don't you have to somehow look a bit into the future? So I still don't understand.
We do. That's why it's called prediction, right? We don't know for sure. It's about probabilities. So we can never guarantee that if we say that something is high risk, we can just say that the probability is high that there's an error in this code. We cannot tell for sure. So there might, of course, be false positives, but that's something we work on all the time to kind of minimize the amount of false positives.
Okay. Thanks for answering that question. Let me just pick the second most. I'll quickly come back to the topmost question after this one. But you mentioned prediction and machine learning, so maybe we'll grab this question now. So which machine learning algorithm do you use in CodeScene?
Oh, that's, I'm really sorry. That's the only question I cannot answer because my business colleagues would shoot me if I answer that one. It's proprietary. In short, we're using, I cannot answer it, unfortunately. We're using multiple different machine learning algorithms depending on, for different purposes and different analyses. But I'm sorry, I cannot go into more details on it.
Sure, of course, I understand. Is there maybe some patent pending that later on we can read about it? Or
Hopefully.
Is that, yes?
Yes, hopefully.
Oh, okay, so hopefully that patent will go through, and maybe we'll have another session in a year or so, and then we can speak about it.
Yeah, then all is public, and I can talk about it as much as I want. So I'm
Cool.
looking forward
Okay.
to that day. I don't like to leave questions like this.
I totally understand. That's fine. And then there's one more reason to get back to you with in a year or so for another talk. So now we have this one with 4 upvotes.
Yeah.
CodeScene can analyze any Git repository or even other version control repositories. And I would actually extend that. So you also mentioned issue trackers. So I would extend that question not only to repositories, but also to issue tracking.
Yeah. Yes. So the short answer is yes. CodeScene can analyze any Git repository. You have to differentiate between CodeScene.io, which is the SaaS version. Currently, it only supports GitHub. Starting next month, we will integrate directly with Bitbucket as well. However, the CodeScene on-prem version, which you deploy in a private cloud or data center, or your own data center, can work against any Git hosting. So it can be GitLab, Azure DevOps, it can be your own Git server, it can be a Git repo that's just local on your disk, anything. There's no limitation.
Cool.
When it comes to other version control systems, like Mercurial, Subversion, then you can analyze those as well. I've frequently done that. What we do in that case is that we set up an automated conversion to a read-only Git repo, and then we point codes into the converted repo. And talking about issue trackers, we integrate with, let me see so I get it right. We integrate with GitHub issues, of course, Jira, Trello, Azure DevOps, and we're going to build support for a bunch of others as well in the near future. So Rally, for example, and there might be some other ones as well. So we add them as we go along.
I think GitLab is another prominent one. I mean, it's also an issue tracker.
Yeah, it is. So we're looking to cover as many of those as we can.
I guess it's a lot of work, but yeah, quite useful to have it.
Yeah, it's not so much work actually. It's more about priorities, right? So we have a bunch of other features that we right now find are more important, but we definitely want to go there. So it's CodeScene is an evolving product. It comes out in new major revisions every second month. So it's far from done.
How many people are working on it in your company?
So I think we are in total we are around 11, 12 people. Not all are doing or coding, of course, all the time.
Yeah, sure. Okay, so the next question is currently being edited. So I guess we'll get back to that, and I'll grab this one. What parts of the source code, as opposed to metadata from version control, does CodeScene look at? Anything language specific?
Oh yeah, yes. So CodeScene has native support for, there's a full list on our webpage. I think it's 25 programming languages where we have detailed knowledge of the language. And we need that to calculate code health. The code health metrics are language specific. So we need to parse the source code and we need to understand it in order to calculate the code health metrics. And also the X-ray analysis that I showed you is also language specific. And this is actually quite fascinating because it's one of those aspects I would love to do a technical talk about sometime in the future, because the reason I showed you gc.cpp as one example was that because that's one of the hotspots I use as performance benchmarks for our parsers. Because if you take a typical, these days there are some very good C++ parsers that are open source that you can use. The problem with them is, for our purpose, is that they require the software to be buildable. You need to be able to compile it. And that's something we cannot guarantee with version control data. Sometimes you have versions committed that contain a syntax error or some header or dependencies missing. And it's also the case that if you look at something like X-ray or CodeDelph, what we do is we pick out all revisions of a piece of code. And it might be hundreds of revisions. You might have 500 revisions of a hotspot. And we need to parse each one of those revisions. meaning we're not parsing one file just once. We're parsing the same file in different versions 500 times. So our parsers have to be extremely quick. So even if you have a modern C++ parser and it takes, I don't know, I'm just pulling a number out, 1 second to parse a monster like gc.cpp, 1 second is way too long in our context. So we have to spend a lot of effort optimizing those parsers so they're really, really quick and can work even in the presence of syntax errors. So I hope I answered that question.
Yeah, I think you did. So I was wondering whether you are using some intermediate representations that would maybe improve performance, and also you wouldn't have to do it individually for for the languages.
So yeah, of course. Yeah, that's one of the things we got really well designed in CodeScene under the hood. You cannot see it as an end user. It's almost a shame, but that's the part of CodeScene that I'm most proud of, that we can add support for a new language fairly quickly.
Cool.
We basically write a parser that translates it to our intermediate format, and that's what CodeScene itself operates on. So the rest of CodeScene is there and ready. We just need to kind of plug in the grammar.
Nice. Great. Okay. So I wonder whether we should take the next question, the upvoted one, or yeah, let's take it, because you can probably talk for hours about war stories, but anyway,
Yeah.
Let's it's the most upvoted one, so let's ask that one. What known projects use CodeScene? Are there any war stories, for instance, of bugs found or improvements made with the help of CodeScene?
Yeah, so there are lots of open source projects. I think we have 10,000 open source projects using CodeScene. We have always been, we're using open source ourselves, and we wanted to give something back to the community. That's why CodeScene is free for open source, and it's always going to stay that way. I can guarantee that. Great. So there are lots of open source projects. We also have lots of well-known commercial projects. I'm not allowed to talk about most of them due to NDAs and customer confidentiality. If you go to npr.com and click on reviews, you can see some of the large companies that are using CodeScene today. And they use it at scale, thousands of developers in their day-to-day job. And yeah, I have a ton of war stories. Let me share just one, because I think it really nails what hotspot analysis can do for you. So this was a couple of years ago. I joined a client to do a hotspot analysis on a gigantic code base. We talk about 20-25 million lines of code, thousands of developers, really everything really large scale. And we've quickly identified a hotspot that really stood out. It was, so we connected some Jira data and figure out that this hotspot was also, because what CodeScene can do is can take Jira data and break it down to file level. And you can see that there were a lot of costs, a lot of hours spent on maintaining that code, adding new features to it, improving it, and so on. And you saw the code health score kind of just went downhill into the cellar. And you also looked at the complexity trends, and they kind of went through the roof, right? It was growing in all kinds of directions, getting worse, and costing a fortune. And when I presented that finding to the team, they were kind of a little bit shocked, because that was software that they were actually no longer using. It was a supporting tool that they had stopped using a year ago. They had an open source alternative that they used instead. But nobody cared to tell the team developing that one. So they kept adding features, executing on a backlog that they accumulated for years. So by doing that hotspot analysis, you can immediately identify a very clear cost saving, and you can now shift that team to do something that actually makes a difference for the business, which is more fun for everyone.
Yeah, that's a really good war story. And I guess if you have some kind of bad some project going south, and you have to determine whether to shut it down or not, that's a really hard decision, and I guess that's also where CodeScene really helps.
Yeah, definitely.
Okay, so these were the. So we have 3 questions left with low upvotes. But I would suggest, if you still have time, let's get them all through. Okay.
Yeah, sure. These are smaller ones, so I'll be happy to do that.
Okay, great. So can CodeScene filter by time? For instance, only look back 5 years. There might be some legacy code that you just accept that it exists and focus on improving the hotspots in the newer code.
Yes. So in CodeScene, you have full control over how much information you include. And CodeScene tries to be smart with suggesting an interval. So in general, most people tend to just use development data over the past year.
Oh,
so
okay.
Because hotspots, it's my experience is that most really problematic hotspots that try to stay where they are for years. So you find a really troublesome hotspot, it's very likely it was a problem already years ago. But in several other code bases, the hotspot kind of tends to shift a little bit. So it typically makes sense to just include the past years. You also have full control in CodeScene. You can say, for example, exclude this part of the code from the analysis, or prioritize this part of the code, stuff like that. You can give contextual input. When it comes to other aspects of CodeScene, like, for example, I talked a little bit, I never showed it, but I talked about building knowledge maps, analyzing teamwork and organizations. And when you use that, it's a very different issue, because there you typically want to include the full available history so that you can figure out what does your knowledge distribution look like.
Yeah,
So in a CodeScene analysis, you typically have several different analysis time spans for different analyses, but it's all automated.
Okay, cool. I wonder whether there's some really good machine learning in those decisions. You mentioned smart a couple of times. I'm just wondering. Anyway, so another question I have directly to the as follow-up. You mentioned some trends for some metrics. So I guess for those metrics where you only look back 1 year, that would be some kind of sliding window of 1 year.
Yes, exactly. That's how we configure it. So you say always look a year back, and that window kind of moves with time, right? So it's
yeah.
Yeah.
Okay. So second to last question, does CodeScene also look at the issue tracker to compute metrics, or more generally find hotspots? See example discussion on recognizing gc.cpp.
Yes, I kind of covered that question when I talked about the other integrations to Jira, Trello, GitHub issues. So yes, we do that. And in fact, it's an important metric that I find particularly useful when communicating to non-technical stakeholders, because they tend to understand the hotspot concept. It makes sense to them, and it's a positive message because it means we don't have to fix all our technical debt. We can just focus on the hotspots. So I tend to like it. What I tend to do is I also tend to talk about code health, but that's a little bit harder to understand for non-technical stakeholders. What to always understand, however, is a defect trend that goes upwards. And since CodeScene operates on historical data, you don't have to run CodeScene for a year to see the trends, right? You can run it just once, and CodeScene is going to generate the trend backwards. So I think this integration with issue trackers is really important.
Yeah. Do you also have some kind of intermediate representation or common ground for issue tracking, or are they just so different that some common representation is not possible?
We do have a common representation. They are very different. It's an extremely challenging integration.
Yeah, I believe so. Yeah.
You look at things like I don't know, Jira. They have different APIs for their on-prem versus their cloud version. So we basically need 2 Jira integrations, not one, right? And it's a lot of things like that. They are quite tricky.
Yeah. Okay. Final question. How can you test your code? I think this is quite difficult.
Yeah, me too. I also think it's difficult.
Yeah. So actually, I don't understand. Maybe the one posing the question, or maybe Adam, you understand it, but I don't know if dynamic testing is meant or the static analysis. What do you think?
Yeah, I don't know. I interpret it more like a design thing. I can tell a little bit about how we work at CodeScene, because testing has been one of my interest areas for a long time. In fact, I'm part of a research project called TesTomat. It's a European collaboration project on research on test automation. So I'm really into that area. And we basically use a combination of techniques. So we have, of course, we run CodeScene on CodeScene itself, which kind of helps us identify those parts of the code where we really benefit from a good test coverage on multiple levels, like the hotspots. We also use, yeah, exactly. We do that. It's actually great because, and then we also use some static checks. There's a lot of good static tools depending on what language you use that we also benefit from. And then we have lots of unit tests, and unit testing is really challenging. And I think that the good thing with unit test is that it really helps you emphasize your design. So when something is hard to test, it's almost always a design problem. And then we also have integration tests, and we are also automating certain end-to-end tests. And despite having a very high degree of automated test coverage, we still need to have manual exploratory testing as well, because there's so many things that I think a machine just cannot find, in particular not in a complex application like CodeScene. We have multiple integration points and dynamic user interface and stuff like that. So I agree. I also find it hard to test code.
Yeah, me too. So I've been working on some static code analysis tool, and I found testing there also quite challenging, especially if you have bad formed code. But of course, you still want your tool to be robust and handle it somehow. So you also have to deal with code that doesn't even compile. I think you mentioned that also before. And that gets really extremely challenging. And you can do that with unit tests usually. So yeah.
In fact, I have to add one of my small short war stories here. When we worked on developing our, in particular, our C++ parser to implement X-ray and CodeElf, we used the gc.cpp, like I mentioned, as one of our inputs for testing, as one of our baseline sources. And we kind of noticed after a while that we keep getting an error notification from our parsing code that there is a syntax error, right? And I kind of, I never trust myself. So I spent a lot of time trying to debug the language grammar. And I kind of couldn't find an error there. So then I finally looked and investigated the source code in more depth. And I found out that there was actually a syntax error in gc.cpp. However, the code still compiled because that syntax error, it was a misplaced curly brace or something quite trivial, but it would definitely fail a compilation. The reason it seemed to work was because it was guarded by an if-def. So the moment they would have, the moment they would enable that flag, they would have gotten a build failure. So I kind of patched it up and sent a patch, and it got accepted. So I'm actually one of the proud contributors to gc.cpp.
Congrats! And how much time did it take to spot that bug?
Oh, so the bug itself didn't take that long. It took maybe 5-10 minutes. It was pretty easy, but I probably spent 2 days debugging my grammar before I even considered another potential issue.
Yeah. Cool. Okay, so I don't know if there's somebody still writing. That just popped up a new discussion item, but it's empty. It is almost 9 p.m. I think you have answered a lot of questions already. We had a great presentation. Thanks again, Adam. So I suggest we call it a day. Thanks a lot, everybody, for joining, and especially you, Adam. And I hope we'll have you back in a year or so.
I hope so. And thanks a lot. It was really nice. And thanks for all the questions. I appreciate it. So take care, everyone. Hope to see you around.
Yeah. Bye.
Bye.